and mechanical contribution to health. Then we have 2 more lectures, and then you're free for problem.
All right. Good morning, everybody, and happy 4th of July. Well, it is 4th of July, right? So, well, I hope it will be a happy 4th of July, I guess. at least I'm on my talk to only induce happiness and nothing else, right? Okay, so I want to do a little bit of recap before we get to, before we continue where we left off. So last discussion, we discussed, rigidity percolation, how to characterize rigidity of networks, and we said we can do this using rigidity percolation, right? And before we actually did any calculations, we said that, well, for central force networks like spring networks, we can do a simple Maxwell counting, right? Which was basically you count the total number of degrees of freedom, right? Which is n times d for a lattice of n nodes in d dimensions. You count the total number of constraints, and then, basically just at the cusp of rigidity, these two things should balance each other. And this gives you the threshold for this rigidity transition, right? How, what fraction of bonds need to be occupied before your network will be rigid. It also tells you about what is the critical coordination number. So the critical, number of nearest neighbors that this lattice-based system must have before it's rigid and so on. And then we did this effective medium theory, right, for a spring network. And basically what the effective medium theory does is it says you take a disordered network where some of the springs are missing, and we want to find an equivalent ordered network which has all the springs, so that if you were measuring the rigidity of these two networks using an apparatus like a rheometer, it will measure the same rigidity, right? So what do these alpha m's have to be so that the overall rigidity, mechanical response, if this network is the same as of this network, right? And the way we did this calculation, we said that, well, what we will do is we will start with a completely ordered network, and each of the springs have a spring constant alpha m. Then we will sort of apply tension in all directions so that all bounds are stretched by the same amount, right? Then we said we are going to replace one of the springs by a different spring of a spring constant alpha, right, instead of alpha m. And then we wanted to know, so what is now going to be the extra displacement or deformation of the spring, because we have replaced it by a different spring constant. And to find out what that extra displacement or deformation is, the way we do it, we first say, okay, what is the virtual force that would have brought the spring back to its position before we replaced it? That's this guy. And if we divide it by the overall, stretching elasticity between these two nodes, which is this guy, right, in the denominator, that gives us this extra displacement, delta U, right? And then we said, okay, so now if we do this, for the entire network, right? So basically we are, doing this over the entire network. We are replacing the spring constants alpha m by either springs of spring constant alpha or by nothing, 0, right? So now you have a network of springs or no springs, right? And the fluctuations, these extra displacements, these are going to have different, they're all going to be small, but they will have plus or minus signs and different magnitudes. And if you take a large enough system, if you average over the entire system, then this extra thing should go to 0, right? And then, so we write down this integral. This is basically the displacement of a spring, and then this is the probability distribution. So we are basically saying we are replacing springs, with a spring constant alpha with a probability p, and then the probability that there is no spring at all is 1 minus p, right? And that gives us an equation like this, if we do this and then solve this.
Wouldn't the alpha effect change when you replace one bond? Because this equation will do for one bond, right? Replacement of one bond. Wouldn't this change when you replace n number of bonds?
So that's why we are multiplying by this probability distribution, right? So this term is going to have, this will break up into two parts. There will be one part where basically it's this delta function is acting on it, and there is going to be another part where it's coming from this, right? So the first part will be basically alpha m minus alpha divided by alpha m by A star minus alpha m plus alpha times P, and then plus you will have alpha m minus 0 divided by alpha m plus A star minus alpha m plus 0 times 1 minus P.
But this like A star would change for this like network, right? Because once you keep on removing.
No, so A star is a property of a completely ordered network.
But we assume that the alpha effective for one bond replacement is the alpha m by A star thing. But when we replace a lot of bonds, then wouldn't that change the effective?
So so A star is a geometric factor. So what is A star? A star is basically, let's go back to the figure. So A star is basically in a fully ordered network. All the springs are present. What is the effective stretching elasticity of these two nodes, right? So A star basically will not so it's a geometric factor that is going to come in from there, right? So in this case, it's not going to depend on anything else, you replacing anything or not, right? So yeah.
But that's the thing, like in the.
So alpha effective is going to depend on the replaced bond, but A star is not. So today I'm going to show you the calculation for A star, and so A star itself is going to depend. It's for a completely ordered lattice, right? With all the bonds present, all the spring constants same, and what is then the elastic, stretching between a pair of nodes, right? So it gives us that. Yes. Yeah. Yeah. So the thing is, you remove bonds sort of uniformly and sort of randomly. And yes, there might come a point where you have removed all the bonds, right? So.
Are you saying that even though all the bonds, say you replace just like the bond spring constant alpha, like the empty one, when you're removing that last bond, the alpha effective would still be alpha m divided by alpha star.
No, this is only for one bond situation. This alpha effective is only for the effective elasticity between a pair of nodes. Right. So you don't do things sequentially, right? So it's not, we are not doing things sequentially here, right? So yeah. I mean, mathematically, yeah, so this A star essentially, once again, it basically just tells us if you have a completely ordered lattice, all of the spring constants are the same, which is alpha m, right? If I ask you then, what is the effective elasticity between a pair of points? What is that? And that is going to be alpha m divided by A star, right? What A star is, we don't know yet. I'm going to show you the calculation for the dynamical matrix and how we define A star, and you will see from there, right? So, yes. Yeah. Yeah, so delta UM is initially you are applying a hydrostatic like tension or compression, let's say tension. Every bond is stretched by the same amount delta UM. That is something that you have applied, right? And the small delta U is on top of that, you will have an extra displacement of this particular bond because now you have replaced this spring by a different spring constant. As a result, this particular bond will either stretch or compress depending on whether the spring constant is larger or smaller than all the other spring constants. So this delta U is an extra fluctuation in the displacement, which is on top of this overall displacement that you had applied in the beginning. So this is different. So we don't know how to calculate delta U directly, right? We don't know what delta U is. So the paper posits one way to calculate delta U is first think of, so what happened here is that we replaced a spring of spring constant alpha m by a spring constant alpha. If you want to think of a virtual force, not a real force, a virtual force that would allow this bond, let's say the bonds moved by a certain amount, that will bring the two bonds back to the same position where they were before the replacement of the spring. What should that force be? That virtual force should be this delta U, this thing, times the difference between the original spring constant and the new spring constant that you replaced it by. So then if you apply this virtual force on this bond and divide it by the effective stretching elasticity between these 2 points, then it will give you this extra displacement. Because we cannot calculate what is this extra displacement. This is one way of calculating this extra displacement. And then what the paper is saying is now if you replace all of these bonds, some by alpha and some by 0, and sum over all of these extra displacements over the entire network, so long as you have a large enough network, this entire thing should average to 0, right? I'm going to wait a little and wait for you guys to absorb this. Can you speak up a little loudly? No, when you apply all the virtual force is supposed to do. So as a result of replacing the spring constant, the 2 ends of the bond had moved away, stretched or compressed compared to all the other bonds, right? This extra force is going to bring it back to where they were, the 2 ends of the bond, before the replacement of the spring, right? That's why it's proportional to the difference between the two, because that's what caused, this difference is what caused the 2 nodes to, move from where they should have been. Right? Other questions? Yes. No, this is above the percolation threshold, because the answer you'll get a negative answer below the percolation threshold, which is unphysical. So this answer is only valid for above the percolation threshold, at and above the percolation threshold. It will give you the percolation threshold. As you go below, you will get a negative answer, which is not a physical thing. It basically just means it's 0. The theory is not valid below, right? Other questions? Okay. All right, so this is what we did. So we get an expression. So basically this term, you can write it like sum of 2 terms, like I mentioned. One term where you set this alpha prime to alpha and multiply by p, and the other where you set alpha prime to 0 and multiply by 1 minus p, right? Then if you reorganize everything, you will end up with something like this guy, right? And so one of the things you can immediately notice is that when p is greater than a star, when p is less than a star, this thing is negative. So that doesn't mean anything. That's unphysical, right? So this solution, effective medium solution, is only valid when p is greater than or equal to a star, right? And a star basically gives you PC, which is the rigidity percolation threshold, right? So that's at p equals or PC equals a star, it will be 0. And then at PC greater than a star, you will see like it will have, in this case, a linear, right, dependence. Okay, so then, we had started talking a little bit about what is a star, and I'm going to talk a little bit about what is the dynamical matrix, how do we calculate a dynamical matrix, all of these things today, right? So a star is a geometric constant. It's a property of the network topology, right? What is the network? What is the dimension of the network, right? What is the coordination number? How are the springs arranged? All of that stuff. And it's the property of a fully connected or ordered network, right? So it relates the geometry of the lattice to its rigidity, and it's evaluated in terms of the dynamical matrix. I will show you what the dynamical matrix is and how it's calculated. So, but the definition of A star, if you go through the paper, you'll see that what it comes out to be, it's 1/3, and it's 1/3 in this case because it's a triangular lattice, right? So 1/3 is coming from basically D by Z. So D is 2 dimension, and Z is 6. So the 1/3 is coming from that. And then it's the trace of the full dynamical matrix multiplied with its inverse in this case. And I will show you what the dynamical matrix is, but this thing, even without doing the calculation, this is a unity matrix, right? And 2D, this trace is just 1 + 1, 2. So this A star comes out to be 2/3, right, for a spring network. Yes.
Going on, is there a way of understanding the EMT calculation as like a coarse graining, like a IG type calculation of like
Yeah, so it's
over a big region of bond and then shrinking it.
so this is more of a mean field. So it's not RG. RG would be a more sophisticated calculation, and you could do an RG for systems like. So when I was a postdoc, when I was doing the semi-flexible networks, I initially wanted to do an RG or a replica field theory. And my advisors were like, you can just do a mean field theory. Why do you want to do an RG for this? That's not necessary. So you know. Yeah, so here it basically is just telling you the effective, you know, you have a very disordered network, and it's telling you about the effective spring constant or effective bending constant or effective shear modulus of the network, right? If your disordered network were basically just an ordered network of springs or filaments, etc., then what would be the stretching or bending elasticity of those filaments, right? So I think that's, I would say, the best way to think about it, right? So. But yeah, no, my initial, so, you know, when we are students and postdocs, we want to do calculations that are sort of, I don't know, attractive and sophisticated, but sometimes they're not necessary. And in this case, you know, this particular thing, it was, but you can still do a lot of scaling analysis to, you know, I'm not going to go over that in the lecture, but like the approach to criticality is on its own a very interesting property of these kinds of systems. And how would it approach criticality? And you know, and then when we see the bending networks with bending, you will see that there are actually two interesting points. It's not just the rigidity percolation threshold, but there is also an isostatic point where, you know, interesting things happen, right? So. All right, so a little bit on the dynamical matrix for those of you who are not so familiar with it. So let's say I have the energy of a system, right? And I can basically Taylor expand out my energy, right, about the structural equilibrium coordinates, right, for the system. And usually we do this for systems which are sort of lattice-based, right, where your, you know, atoms or particles will vibrate about their lattice positions, things like that, right? So if I Taylor expand this energy, I start with the equilibrium energy, then there is a first order term, there is a second order term, a third order term, and so on, right? You all know this? This is everybody good with this? So now, because we are at equilibrium, this first term is going to go to 0, right? Because no forces, they will all balance each other. So then we are left with, you know, we start with this, we have the second order term, we have the third order term, etc. The second order term, I have written it out in a way, right, in terms of, you know, the displacement. This is basically this guy, right? This is, you know, writing it, the u square, I'm writing it like this, and this second derivative of energy, you know, you can write like this, right? And if we are thinking of this in the context of a harmonic sort of, you know, approximation, then the third order and higher order terms are all 0, right? We can ignore those. So we are thinking of a harmonic approximation. Does everybody know what a harmonic approximation, or do most people know what a harmonic approximation is? Those of you who know, do you want to tell your friends in a few words how you would explain it? Does anybody want to volunteer? Yes. Speak loudly so your friends can all hear you. Yeah, so if you're thinking of nodes or points on your lattice, right, you can describe their vibrational motion using these modes, normal modes, right, which are all independent of each other. And for each of these guys, you can fit their vibrational motion, like your friend said, with the local, you know, parabola. So locally, it's a harmonic approximation, you know, it's a harmonic well, right? So in that approximation, we are going to neglect all of these higher order terms. We will only keep this second term. And I'm writing the second term like this, right? Yes.
The subscripts on the U.
Yeah. Yeah.
You need to specify both the atom and the unit cell, since on a triangular lattice, doesn't each unit cell only have one atom anyway?
This is a general description. I'm just writing the most, because I'm just telling you about what a dynamical matrix is, right? So I am just writing it in terms of, you know, all possible indices that you would need. So this guy, this is essentially, we can write it. So this guy is basically the matrix of all the force constants, right? So it's the second derivative of your energy, right? All of those terms. Or you can write it in terms of the first derivative of the force, right? The gradient of the force, like this, right? So, and the dynamical matrix is essentially the Fourier transform of this force constant matrix. I'm going to wait and see if you guys have questions or if you want me to explain anything. So the force constant matrix, like if you had one spring, you have spring constant is your force constant, but now you have a network of springs, and the network has its own topology in terms of number of nearest neighbors, the way they're arranged in X and Y or in 3 dimensions, different dimensions, etc. So you cannot describe your system just by, one spring constant if you have a network like this. So this matrix is a matrix of force constants that tells you about the whole, XX, XY, YY, YX, different what's happening, right? And the dynamical matrix is the Fourier transform of this thing, because often in physics, it's useful to do calculations and think of things in momentum space before getting back to real space. And the other reason is somebody had asked about the dispersion relationship in last class. And you can also use, you can write down the eigenvalue equation. You can write down the dispersion relationship and see how the vibrational frequencies are related to the dynamical matrix, right? So, yes. Yeah, so I'm going to, in K space, normally what you do is it's enough to just sum over the first Brillouin zone, right? So we usually sum over the first Brillouin zone. And so if you want to get the vibrational modes, I forgot who had asked about the vibrational modes in last class. You had asked about it. Then you can relate, you take a solution which is of this form, right? And then you use it to get this relationship. And then you can relate you have your dynamical matrix, and these guys will give you your vibrational modes. Marcus, you have a question? Sorry, can you speak loud? What do you mean by what is it?
Variable that
You were Fourier transforming the force matrix, right? What do you mean by what's the variable? I mean, so you are going to, so the force matrix, I'm going to show you a calculation slightly. So it will have like, so you have, let's say, your deformation energy, right? So in real space, you will calculate the XX, XY, X, Y, Y components from the deformation energy. That's your real space thing of the force matrix, right? Then you're going to take Fourier transform for every single bond, right? And sum over different bonds, right? With that kind of a solution.
I don't understand
The position dependence comes from, because when you do this for the entire network, so let me show you an example for the, so let's say this is my triangular lattice spring energy, right? In this case, when I write down the dynamical matrix, first in real space, and then I take a Fourier transform, in real space, it's just going to give me Rij, right? If I take second derivative of this energy with respect to the displacements, the Uijs. But then these guys, you have the one is for the self term when I and j are same. And when I and j are different, these are the not self terms. And then you have to sum this over all of these 6 bonds, right? So the spatial information is coming from the spatial coordinates, etc., of all of these bonds. Alpha M is the effective medium spring constant, yes. So in addition to alpha M, you will also have other things that are here, right? Because of this. So it's not just alpha M anymore. So the Rij's, yeah, and then you're taking this Fourier transform, right? So the positions, because you are summing over, so so when you have this bond versus this bond versus this bond, this bond, this bond, the Rij's for all of these different bonds are going to be different, right? So yes. So a small q would correspond to, I guess, if you're going into wave number space, you could think of it that way. Yeah. I mean, small q, basically, you're looking at a long wavelength, kind of, yeah. So, sorry, what was your question again? So this is, we are assuming a displacement of this form, right? So the solution for the displacement, we assume it of the form of this kind of a, plane wave thing, right? So, okay. Yes. So it's the solution is basically the displacement field, the displacements, we take it, we substitute it in the thing, but in the end, the D of Q that we get is a Fourier transform of the force constant matrix, right? So we are using this to get a Fourier transform of the force constant matrix. Right. 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 Yeah, so the solution, yeah, so it's the U's that are being Fourier transformed. But in the end, the dynamical matrix that you get, that matrix is a Fourier transform of this initial, this guy, right? So. This is not a number, right? This is also a matrix.
It's not a tensor field.
Right.
So you can't Fourier transform. How do you Fourier transform the matrix?
So you calculate each of the components. So, so here, for example, you are going to get each component of this matrix, in Q space, right? Yeah, so let me see if I. Okay. Sorry. I've written it as XX, but this should instead be KX, KX, KY, KY, KX, KY, and so on. So these are going to be the four terms of your dynamical matrix, right? Where you have a term which is KX, KX for the spring part. And then I guess I should show you this in matrix form so you know what this actually looks like. Sorry. Okay. So this is what this dynamical matrix, if you were just focusing on the spring, would look like, right? If I did the full I'm not doing it on the board because this is not, it would be messy if I tried to do this on the board. And we don't have bending in this lattice, but if we had bending, then there will be an additional stop that will come in. Yes.
maybe like a 1D chain.
Yeah, yeah, yeah. So
So I don't really get.
So for 1D chain, it's just a 1D thing. That's kind of simple, right? Then you just have one bond, right? So in that case, you would only have, so in that case, what you would have is, let me go back to my slides.
I just mean formally the calculation rate.
So for a 1D chain, you will just have one term. You're not going to sum over all of these bonds, but you will, if you have, well, you will sum over bonds, but they are all going to be bonds in the same chain. You are not going to sum over different directions or anything. So that's a much simpler situation, right? So you still have a one because the one is coming from the self term. And then this is coming from the case where you have a bond, right? The ijth term, right? And instead of a dot product, this is just going to be k times, the unit vector is in the x direction. So it's just going to be kx times your bond, so this is not the unit vector. I think this has to have length scale. So this will just be the lattice constant. Okay. Pij is whether a bond is there or not. So it could be either 1 or 0. So it's 1 if a bond is there. It's 0 if a bond is not there. Yeah, so no, this is the energy. This is what the energy looks like. When you calculate the dynamical matrix, you don't really worry about the Pij. You are just taking a derivative of this thing twice with respect to Uij, right? Which is why you end up with an Rij thing here, right? So if I were writing this thing in real space, not doing a Fourier transform, then the components of the dynamical matrix would just be Rij. So there will be 4 components. There would be Rijx, right? So just multiplying the x component of Rij, Rijy, Rijy, and then Rijx, Rijy, and Rijy, Rijx, right? And then the 1 is coming from the thing is when you are taking a derivative, if I and j are same, that will give you a 1, right? So that's coming from here. Basically, if this guy is 0, right? So yes.
Isn't the dynamical matrix coming from H94 or the PAG?
Because the dynamical matrix is a property of the fully ordered network, like your friend was asking and I was telling you. The reason the P is still here is because I wrote down the energy for the full disordered network. But the dynamical matrix, we calculated for an ordered network where all the spring constants are alpha n, right? So you could think of it as a matrix of spring constants, right? But we are just doing this calculation in Fourier space. But for a spring network, this calculation is actually quite simple because no matter what my dynamical matrix is, I will end up getting a unit matrix, right? And then the trace of that in 2 dimensions is just 2. So then I'll just get a 2/3 here. But for when you have bending or angular springs, then things become much more complicated. And I'm going to show you a little bit of that as well.
Why is that a star?
Sorry? How did we arrive?
I see that we define something a star as this. Why is that the same thing?
How did you? Why? So I'm showing you how to calculate a star. Because the thing is, so this is the part of the calculation that I didn't go through because then I will have to derive the full paper that I showed you guys, right? So if you go over the paper, this is how a star is defined. If you look at the forces, right? And if you try to calculate what the forces would look like in terms of a star, that will give you what this a star is, right? So. Because I didn't want to go through just one full paper, but show you what happens for spring networks, what happens then for semi-flexible networks, and what happens when you have anisotropy or structural correlations, all of that. If I just derived this one paper, then that's what I would do over 3 lectures, which is not something I wanted to do. Yes. For a spring network, A star will always correspond to PC. But when you have a semi-flexible network, we will see that it's a little bit more complicated. Yes. This is going to be true even if you had a square lattice. What is going to be different for a square lattice? This equation will be true for a square lattice or a Kagome lattice, whatever lattice, right? What is going to be different is A star itself is going to be different, because remember, A star depends on the geometry of the lattice. Yeah.
At what point
It came in here. Yeah, it came in. So when I wrote down this term, this is still going to be the same at a square lattice. However, because I have a triangular lattice, this sum is over these 6 bonds. This is what the unit cell looks like. I'm summing over the bonds in this unit cell. But because in reciprocal space, the dual of a triangular lattice is a triangular lattice, right? But, yes. Yeah, yes. And that's again, because for a triangular lattice in reciprocal space, that is also a triangular lattice. But for a square lattice, this will have a different geometry. So the sum will be over different bonds. For a Kagome lattice, the sum will be over different bonds. So this sum is where, when you substitute the various Rijs, that's where the topology or the geometry of the lattice is coming in. Right. So for spring case, that will not different, because it's D multiplication of D times D inverse, which is just a unit unity, right? So, but if you had a different kind of situation, like I will show you in the semi-flexible filament case, then things get more complicated, right? So, yeah. Well, no, you'll not get, sorry. There is something which is you'll not get so you will not get 2/3, because where is the dynamical matrix I wrote down? This thing, prefactor here, is D by Z. And D by Z for a triangular lattice is 1/3. For a square lattice, D by Z is 1/2, right? So yeah, so you might have like, okay, where is this 3 coming from? That's because Z is 6 and D is 2. So this is 1/3. So for a square lattice, A star is 1, right? Which basically means that for a square lattice, all of the bonds, even when all of the bonds are there, you're still just at that threshold, right? So which is why square lattice of just springs is really not a good situation. You will have to connect next nearest neighbors with something to get it to be, rigid, right? So Kagome lattice, you'll get the same thing. But for Kagome lattice, once you introduce filament bending, then things are good. But if you had a Kagome lattice of only springs, you will not have rigidity for the same reason. For a spring network, among our usual familiar lattices, only the triangular lattice is sort of, is good. Yes. Yeah. Because I should have, instead of writing it as 1/3, I should have written it as D by Z. And D by Z is 1/3 for a triangular lattice, because D in 2 dimensions is 2, and Z in 2 dimensions, Z for a triangular lattice is the coordination number is 6. So that gives you a 1/3. If I was looking at a square lattice or a Kagome lattice, D will still be 2, but Z would be 4. So that will be a 1/2. So I should not have written 1/3, because I was doing this calculation for a triangular lattice. I wrote it as 1/3, but I should have written it as D by Z. Yes.
Yeah, I'm interested in this dependence on the shape of the lattice.
Yeah. Yeah. So the thing is, the shape of the lattice is important because the connectivity, how many filaments or springs are connecting at a given node, etc. So when your network, so in the language of these networks, there are two different limits. One which we call an affine limit, where the network is really quite dense. The density is high enough that a continuum approximation would actually be good. And an affine limit means that it doesn't really matter what length scales you're looking at. You're looking at larger length scales or smaller length scales or different parts of the network. The deformation will look very similar, will look the same. But then there is a non-affine limit when your network is really, really sparse. And in the non-affine limit, if you're looking at different parts of the network or if you're looking at different length scales, the deformation is going to look very different. And in that non-affine limit, a continuum approximation is not going to be a good approximation anymore, right? So the reason we often use these kinds of filamentous network models for these systems and not just a continuum kind of, thing. We still use a continuum model, but it's good to know the validity, right? What kind of conditions are different types of approaches valid? For a very sparse network, your continuum models will not give you the same results because you can assume that, or a network where there is spatial heterogeneity, because, things can deform and behave very differently in different parts of the network or depending on what length scales you're looking at. Well, below PC, you're just in a liquid phase or not a non-rigid phase. But even above PC, I will show you the graphs in a bit when I show you semi-flexible networks. When you're much above PC, you are in an affine regime and a continuum approximation will work. But when you're just above PC, you're close enough to the threshold, then you are sort of in a bending dominated or non-affine regime. But I'm going to talk about it a little bit more in a minute. How am I doing on time? Okay, time is fine. So before we go to semi-flexible networks, you can ask, a spring network is a very idealized situation. What is it good for, right? So somebody might ask that. So here, I think one of the authors of this paper, the last author is actually going to be at the summer school in the 3rd week, so he can tell you more about this paper. But what they did, so they're looking at morphogenesis in zebrafish embryos, right? And during this phase called gastrulation, this embryo goes through a solid liquid or rigid non-rigid phase transition, right? So they were trying to quantify it. So the way they quantify it, these are all the different cells, and they sort of, do a construction where they sort of derive a network, right? Connected network from the cell connections, and they call it a network of springs, and they use a triangular lattice kind of description to show it. And you can see, so for a triangular lattice, this is where basically like 2/3 is the regime, right? If you had plotted your, alpha, etc., as a function of, in this case, they're calling it normalized connectivity, but if you had plotted it as a function of P, you would get at, 67% or something, right? You will get your rigidity transition. It will be a straight line here, it will go to 0 here, and then this, right? And they seem to find that their, experimental result for this solid fluid transition in their zebrafish embryo, so sort of maps within that kind of thing. So. But you should ask, I think he's going to be here during the 3rd week of the school, so you can ask him more about, these experiments. So again, even this idealized spring network can still be useful in understanding, rigidity transitions in real biological systems, right? Yes.
C is something which is non-universal and depends on microscopic details. So like the thing that you want to measure maybe is like behavior near the critical point, right?
Yeah.
Maybe about
in a biological system, that's too difficult, but it can still. So one of the things that is kind of, and I'm going to give you, tomorrow I'm going to talk a lot about comparison with various experiments, et cetera, et cetera. Today, I'm still talking about systems where you only have a network made up of one filament type. There is no background gel. There is no other second network or anything. There is, so I'm talking about less messy situations, which experimentally you can construct by making in vitro systems where you take, let's say, purified actin or purified collagen, and you build a network out of that under controlled conditions, right? So those are the kinds of experiments you can think of to, map these kinds of situations. But in live cells or live tissues, a lot is going on. So what happens is, there is a lot of spatial heterogeneity, which I'm going to talk about a little bit today. Your transition can get smeared out, but one of the things that we think is happening is that a lot of biological systems actually reside very close to a phase transition, especially mechanical phase transitions, which gives them a huge amount of mechanical tunability. Because then by changing just the concentration of elements or how they are cross-linked and arranged, you can change the mechanical response by a huge amount. But at the same time, they don't really fall apart and become, they might become more liquid-like, but they're able to recover and not completely they do sometimes get damaged, but not as often. That's because there are also multiple mechanisms, like biological systems don't really reside in an optimal state, is my opinion. It's not like, okay, this is the, like optimized version. They have a lot of slack. They have a lot of different things in their toolbox so that if something fails, then something else can take over, right? You're asking a question. Well, I think the way to parse this in terms of the language we have been using for our our spring network, what they're calling the normalized connectivity, this is more related to the P's that we were writing, right? And this force against deformation is more related to the force constant, so more would be like alpha m, something like that. And if you had plotted alpha m as a function of P, then it would go to 0 at A star, and A star was 2/3, remember, which was like 0.67. So it would go to 0 around here. And then, so this is sort of the, if you want to map between what I just showed you and the data they are showing, right? But the data really goes quite well with that, right? So, yes. So you should ask him when he comes in the 3rd week. Yes. Yes. Yeah, if you go to 3D, again, your PC, your percolation thresholds will be different. The exponents as you approach the criticality will be different, but you will still see, well, it's not a given that if there is a transition in 2D or 1D, there will be a transition in a different dimension. But in case of this rigidity percolation, let's say if you looked at an FCC lattice, and people have looked at that, you will find a rigidity transition in well, at least with bending, etc., right? If you're looking at it in FCC lattice, right? So, yeah. Okay, so now a little bit related to your homework problems. What if you have a simple anisotropy in the spring network, right? So let's say, the occupation probability in the x direction is different from the occupation probability in these two. I'm calling these both py. So if py, this is different than px, right? How are things going to be different? You can ask first, how will your Maxwell counting going to be different? So now the number of degrees of freedom is still n times d, right? But the number of constraints, remember, it was earlier just 1/2 times n times z times p, right? But now it's going to be 1/2 times, everything is, n is still n, but z, the coordination number, and px are different in this direction versus in these directions, right? So I can write it like this. So this is what my number of constraints is going to be in a network with this kind of anisotropy, right? You all agree? Okay, what is Zx and what is Zy? You are still thinking of this triangular lattice, right? And all the bonds are, not a disordered triangular lattice, an ordered triangular lattice. So Zx is the coordination number in x direction. 2, Zy is the coordination number in y direction, right? So 4. And dimension d is 2, right? So if I substitute all of this, the condition now, by balancing the number of constraints and number of degrees of freedom, is going to be px by 2 plus py equals 1. Yes. Yeah.
Like if I were to flip text, like if I just take this and rotate it.
Yeah. So I am saying is this for this particular, so X is basically just this orientation. I'm calling this orientation of, I mean, it could be any, right? So, you know, so the physics should not depend on that, no. But I'm just saying that if, let's say, one direction you take as some probability and the other two directions, whatever the other two directions, is a different probability. It doesn't really matter. I could have chosen this as this and then those two other directions as the same probability, right? So yeah. So your colleague is saying that, well, what is the meaning of even px or py? Because it's an isotropic system, right? I could just rotate it. So the thing is, it's basically saying you have three different directions, right, in your triangular lattice. In the other two directions, you have a different probability. It's just saying that kind of thing. And this is what the relationship is going to be from the constraint counting, right? You can check. So we wrote a paper, again, 10 years ago. Oh my God. Yeah. So where we had the situation and the spring constants, the spring constant in all the directions were same. And then the effective medium theory, you can see that will also give you a similar relationship. Then you can think of a different situation where these probabilities are not different, but the spring constants are different. And then you can ask, that result you will not get from constraint counting, but you can do an effective medium theory, but with different spring constant in this direction versus the other two directions, and then see what things, what the dynamical matrix would look like, what your, effective medium spring constants would look like. In that case, you should actually not just get one effective medium spring constant, right? You should calculate two effective medium spring constants, one which is in the original direction where it's this and the other for the other two directions, right? So this is kind of related to the homework problem, but I didn't want to do all of it because I want you guys to also try some if you pick this problem. Okay. We have about half an hour left. I'm going to talk about semi-flexible networks where you also have bending in the next half an hour, right? So any questions on spring networks before we go forward? Yes. I think I will do that tomorrow. Yeah. The approach to criticality and some of those things I will do tomorrow when I also talk about, connections to experiments, etc. Okay. Oh. Okay, so I already talked a little bit about this situation, right? So what will happen? We have a semi-flexible network. So in addition to worrying about stretching energy, we also have to now consider bending energy, right? Because it also costs energy to bend filaments. But we are only considering bending along filaments, not angular springs between crossing filaments like this, right? So we say that whenever two filaments cross, there is a crosslink. Crosslink will prevent sliding of filaments like this, but it will allow free rotation. So these angles are not constrained. There's no bending energy for that. The only bending energy is bending for, let's say, if this is my filament, then the only bending energy is for bending of this filament, right? Okay, so then we again write down this energy. The total energy is, a sum of the energy coming from stretching or the spring energy and energy coming from bending. And the distribution of stretching and bending constants is now the stretching constants are still going to look like the spring constants we had previously written. So a bond is there with a probability P. So, your alphas are there with a probability P and zeros are there with a probability 1 minus P, right? No springs. For bending, however, instead of P, you have P P square. Why do we have P square? Because we don't have bending for individual bonds. Bending resides in this model at hinges, right? Which is a pair of bond. And a pair of bond, more specifically, which is initially straight like this, right? So for there to be bending energy or contribution to bending energy, both of the bonds in this bond pair have to be present, right? So that's why it comes with a P square, because each of the bonds have to be there. If one of the bonds is there, then there is no bending. If none of the bonds is there, of course, there is no contribution to bending, and so on. Right? And then I wanted to show you what the dynamical matrix, yes. So basically, this is an assumption of the model, right? So don't think of a real biological system, just in a network, right? So in a network, you can have, like anytime you have a pair of bond that's initially making, in a triangular lattice, right? Let's say when all the bonds are there, you have a coordination number of 6. So you have 3 crossing filaments. So in that situation at a node, you have 3 bond pairs. That's the maximum number of bond pairs you will have at a node, right? But then you can dilute, some of the bonds are missing, etc. So you can end up with 2 bond pairs or only 1 hinge bond pair like this, right? Yeah. So for actual biological system, the filament bending is just bending of the fibers. And here I'm thinking of a fiber as a series of bond pairs or hinges, right? So there is this, then, and they are, which are all sort of contiguous, right? But you can have in actual biological systems where you have 2 crossing filaments. It's very rare that you will have 3 crossing filaments, which is why, so I still kept using a triangular lattice until, the work I'm showing now today still worked from my postdoc until I was a postdoc. But then when I became a professor, I was like, wait, but like this 3 crossing filaments is a bit too much, and maybe triangular lattice is not such a good lattice. And then I started using the Kagome lattice. Because in biological systems, at the most, you will have 2 crossing fibers, and then sometimes even one of them is half, broke, like partially there, right? So yeah. Okay, so now if I want to look at the dynamical matrix, I have to consider a dynamical matrix component or contribution that comes from stretching, which again looks the same as the spring network matrix, right? Because like we discussed, the dynamical matrix doesn't change, right? And this is still triangular lattice, so everything is going to be the same as we did before. But in addition to a component contribution coming from the spring part, spring energy or stretching energy, there is also going to be a contribution coming from bending energy. And this is what that guy is going to look like. Once again, if we take, the second order derivatives with respect to the energy, etc., right? And then we, go into K-space and so on. And then the overall dynamical matrix is the sum of these 2 contributions, one from stretching, one from bending. All right. So then you can ask, how about what will these equations, right, look like if we want to calculate, what the effective medium spring constants are, so we can do a similar effective medium calculation like we did for the spring case, but now both for the springs, the stretching part and the bending part. The stretching part gives me the same kind of relationship as P minus A star by 1 minus A star. Bending part gives me P square minus B star by 1 minus B star. But my A star and B star are not the same as they were before, right? Because for A star, if I did the full calculation, what we would see is that this is not the trace of the full dynamical matrix multiplied with the inverse of the full dynamical matrix. It's the trace of the stretching part of the dynamical matrix, because A star corresponds to the, contribution of the network geometry to stretching between nodes, right? So this is only the DS part, but then the inverse is for the full dynamical matrix. And for the bending, this is for the DB part, and this is for the inverse is for the full dynamical matrix, right? So A star and B star are now different. And A star and B star are going to depend, A star is going to depend on both alpha M and kappa M. B star is going to depend on both alpha M and kappa M. So to get the percolation threshold, we will have to solve all of these equations self-consistently, right? And then we get the percolation threshold. Questions or comments? Yes. Yeah. B star also depends on the geometry of the lattice, but it's telling us how the geometry of the lattice is going to contribute to the effective bending at a hinge. Yeah, because so that's B, the contribution of the geometry to bending, right? The fact that this is all part of a network, and A star is the contribution to stretching. So flexibility of the crosslink, you have to be a little bit, so what do you, when you say flexibility of a crosslink, what do you mean? Yeah. Right. So B star is going to change, but in this case, this is a much more complicated situation because A star depends on alpha M kappa M, B star depends on alpha M kappa M, alpha M depends on A star, kappa M depends on B star. So everything in the end depends on everything because of this coupling, right? So, yes.
So you have two locations for transition. What happens?
You have one, no. So you are going to, so we will have two quantity, alpha M and kappa M. Both of these go through the rigidity transition at the same point. So the way we find the transition, I'm going to come to that in a moment, right? So how do we find the location of the transition in this situation, right? So, okay, yeah. So exactly your answer to your question. So now, so this is no longer, this multiplication is no longer a unit matrix, nor this. But if I add A star plus B star, then this DS plus DB becomes total D. Then I will add A star plus B star. Then that is going to become 2/3 like we had before, right? And then you can say that at the percolation threshold, A star is just PC and B star is just PC square. So then I replace A star by PC and B star by PC square. That is equal to 2/3. Then if I solve for what is PC, that comes out to be 0.457. I'm not assuming, well, I am assuming that this is both happening at PC. Yes, yes. So, well, this is the shorthand, but if I solve those equations like I showed you, I'm just showing you if I didn't solve the equation and wanted to find the percolation threshold, what would it look like? But if I didn't do this, right, and if I solve the equations simultaneously, the self-consistently, you will see that alpha M and kappa M both go to 0 at the same point at PC, right? Yes.
Where the bending energy is 0.
Yeah.
I would expect PC to return to
Yes.
2/3.
Yes.
But how does that fall out of this map?
You can see, so in the limit where bending rigidity goes to 0, you will just have A star equals 2/3, right? And you'll get that. I'm going to show you the curve and you'll see the curve. Next slide. Right? So when bending is 0, if I just calculated G as a function of P, and G, the shear modulus for a spring network is basically just square root of 3/4 times alpha M. So if you know alpha M, you know the shear modulus. So G versus P is going to be at 67%, like we had calculated from effective medium theory, if I had plotted. By the way, we always plot this on a semi-log scale in theory. The reason we plot this in a semi-log scale is because it's easier to see the phase transition. Like you can see that In a log scale, you will not see a fall like this, but on a semi-log scale, you'll see this. And now if in this case, I set alpha to, both of these cases, I set alpha to 1. Here, kappa is 0, I'm putting kappa, right? 0.1, 0.01, 0.001. One of the things you notice is that there are two things to notice. One, the percolation threshold is the same for all of these guys, right? It doesn't depend on what the bending rigidity is. It basically just depends on this thing that we found, right? The other thing to notice is that for the soft, where the bending is really weak, right, these guys, you see there is an inflection, right? And this inflection is happening at the point where it would have gone through with the transition if there was no bending. So what happens is for very weak bending, it starts dipping like this, but then it realizes there is actually bending, right? It's not like bending is 0, so picks up again and then goes through the transition here. This point, the 0.67 is known as the isostatic point, right? That's the point, that's the transition point for just a spring network. And this is the rigidity percolation threshold. So when we study exponents, etc., you can study exponents, what's happening near this point. You can also study exponents of what's happening near this point, right? And remember, I was telling one of you that there is an affinely deforming regime where things deform uniformly, and there is a non-affinely deforming regime where things sort of do not deform uniformly. And depending on which part of the network you're looking at and what length scales you're looking at, things are going to look very different. So the affinely deforming regime is this part, large values of P, where you can see that this G is varying very slowly. Like you can change P quite a bit, but G doesn't change very much, right? So that's the uniformly deforming regime, where if you did just continuum approximations, you will be perfectly fine. But then in this, when you are in this regime, where you're still above the percolation threshold, but your shapes of G are very different, they change quite a bit. Here you're sort of in the bending. So this regime is dominated by stretching elasticity, and this regime, which we call the non-affinely or non-uniformly deforming regime, is dominated by the bending elasticity. And here, a continuum approximation is not going to be as good of an approximation for these kinds of networks and their mechanics. Yes. So that's going to be very hard for biopolymer networks, because biopolymer networks, stretching is always weaker. For biopolymer, stretching is always weaker than, bending is always weaker than stretching. Like if you stretch this, the amount of energy it will cost you is going to be much larger than if you sort of try to bend it. But you can cook up other kinds of, situations where, not biopolymer networks, where you have that thing. And then you can write down an energy with only the bending term, like you said, and no stretching term, and then see what things you'll get, right? So, yeah. So one thing I will mention is that the effective medium theory calculation, to do that, we have to be able to use this harmonic approximation, right? So that's why we are in this small deformation regime where we can make those kinds of approximations, right? Because I am throwing away all of the higher order terms in the energy, right? But if I had really large deformations, etc., I would not be able to throw away all of those terms. Questions so far? Or questions about the differences between the spring network and the semi-flexible networks? Okay, so now a little bit relevance to biology or experiments. So often the kind of networks where, historically people have used these kinds of models, I have also used these kinds of models, are in vitro network actin filaments. So actin is one of the filamentous system that constitutes the scaffolding of the cells, the cytoskeleton, right? So, and there are a lot of different types of cross-linkers that cross-link actin filaments into networks, right? So at least 23 different cross-linkers that I know of. There can be more. And these different cross-linkers might cross-link actin differently. So you can have something like alpha-actinin, which cross-links actin in a very floppy way. So the filaments can keep moving like this, like I was telling you, where the approximation is a good approximation. But you can also have something like filament, which will cross-link them so that they try to maintain well-defined angles like this, right? So in that case, I will have to add an extra energy or extra constraint where, there is also going to be a bending energy for changing the angle between crossing filaments, right? And so there, things will look a little bit different. And then also you can have things like, ARP23, where again, ARP23 is a protein that leads to branched networks of actin near the sort of leading edge of the cell, right? And once again, you have well-defined angles in this kind of situation. So in something like this or something like this, you will have additional constraints because of, constraining angle between crossing filaments. And then you can ask, what would the results? So I'm only going to show you the result inside the paper we wrote. So this is if we just had this freely rotating crosslinks, which is for something like alpha actinin. But if we also have angle constraining crosslinks, in addition to, everything else that we had, which will constrain these angles, then what happens, you have more constraints. So you can obtain rigidity with less amount of filaments, right? Which means that the percolation threshold, the rigidity percolation threshold, is shifting to smaller values of P, right? So even at lower P's, you can reach rigidity, right? Because now you have these additional constraints that came in from these angular, constraints, right? So does that make sense? Just from a point of view of, so you have more constraints, so you need less material to be rigid, right? Because, yeah. You could, it just gets a little bit more complicated and you have to do things more carefully because when you have bending or these kinds of angular constraints, it's not just, bond terms, right? No longer just central force terms. It's like what I was calling a 3-body, right? You have 3 node terms, so you have to be very careful about those things. But you can still do, so long as you're in linear response, you can always do effective medium theory. And you can also, another way to do these things, and I'm going to show you in the next part a little bit, is you write down the deformation energy, then you can apply a shear or a compression or an extension, and then you can minimize the energy. And by finding the energy minimum, etc., you can also calculate the shear modulus. And that is something you can do not only for small deformations, but also for large deformations, right? Yes. So it will apply for in vivo systems, but for in vivo systems, things will get more messy because for in vivo systems, it's not just actin networks. I'm going to talk tomorrow about what happens when you have at least 2 different types of networks, let's say actin and microtubules or collagen and proteoglycans, so when you have multi-component networks. In vitro, it's easy to construct a network made up of 1 filament type because you are doing the construction. But in cells or tissues, you have your networks are multi-component and composite, right? But you will still get percolation thresholds for those, but they will depend on the concentration. And I will also show you tomorrow how to go from this like axes of occupation probabilities to, let's say, concentration of collagen or concentration of something, right? Because ultimately, if we want to compare with experiments, we need to map things in terms of properties that can be experimentally measured. Okay, so in the time that is left, I'm going to show you one slightly special case of what happens when you have spatial heterogeneity, right? So right now, the networks I have showed you, they were disordered, but they were spatially homogeneous. I diluted bonds sort of in a homogeneous way throughout the network, right? But in real biological systems, both how the networks are made as well as how the networks are degraded, there is no reason to expect spatial homogeneity. Often things are actually spatially inhomogeneous. So here, for example, I'm showing you an extracellular tissue. This is in fact for cartilage. These are chondrocyte cells, and these cells are going to make collagen and other stuff in cartilage, right? But you can see the density of cells, in this case, it's kind of spatial uniform, but then you can get regions where, you have cells clustered in one region and not very many cells in other region. So then when they make, a network, there is going to be more material in one region, less material in another region. There will be a lot of spatial heterogeneity. Similarly, if you start with a network and the network is being damaged either because of, stress being pulled or because of some enzyme, right? It's not going to be damaged uniformly throughout the network. You can imagine that more material is going to be missing in some regions and less in some other regions, right? So then how does this kind of, how do we talk about rigidity of networks that have this kind of spatial correlations? How do we study their rigidity, right? So a model that we constructed, this is more recent work, is we said that, okay, we are going to construct a network that has spatial correlations or structural correlations. And the way we do it is, again, we are choosing, sorry, this is a little messed up, Kagome lattice. And we are saying that, but the bonds in the Kagome lattice, we start, when we either fill in the lattice or dilute the lattice, we don't do it uniformly. We say that if a bond is there, the maximum number of bonds it can have in a Kagome lattice is 6, this one, this one, this one, this one, this one, and this one. So we say that if a bond is already there, then we are more likely to fill in its neighbors. If it's not there, then we are not as likely to have its neighbors, right? So there is, we include basically this randomly chosen bonds with a probability P equals 1 minus C, right? To the power of 6 minus the number of nearest neighbors. And then NN is basically whatever is the number of nearest neighbors for that particular bond, right? And the degree of correlation, we can choose how much correlation we want, right? So if we construct a correlated network like this, then this is what we would get. Oops. Sorry. So here, let's say I'm increasing the fraction of occupied bonds. So this is the same value. So this is P, whatever we were describing as occupation probability. For the P, as I increase C, which is the degree of correlation from the previous slide, you can see that there is more and more clustering, right? So again, same P, we are changing C, there is much more clustering, right? So this is how you can build stuff, networks where you have spatial correlations, right, for a given P. So then we wanted to find out what would be the shear modulus for these kinds of networks. So doing this calculation with an effective medium theory is harder, much harder. So we did an energy minimization, like I was telling you. So once again, we will write down deformation energy for this thing, right? And then we will apply, let's say, a small shear. We will minimize the energy, right? And then we can calculate, in the linear regime, the shear modulus is basically 2 times the energy density divided by square of the strain, etc. We can calculate the shear modulus, plot that as a function of P, right? And what the shear modulus looks like is the following. So this is again P, the occupied bond fraction. This is the normalized shear modulus. So we take the shear modulus, divide it out by the shear modulus for the completely ordered lattice when all the bonds were there, so that the maximum value will go to 1, etc. And what we find is that, so for zero correlation, C equals 0, this is where my percolation transition would have taken place, right? If they was completely homogeneous. And this is a Kagome lattice, by the way, not a triangular lattice. So the percolation is a little bit different, right? So now as I increase C, 0.2, the percolation threshold moves more and more to the right. So that's because as I have more and more clustering, you can have a path for mechanical forces to be transmitted with less filaments, right? Because things are clustered. However, you can see that once it goes to 0.6, still moves this way, but then when it goes to 0.8, it moves back in this direction, right? So it seems like some correlation is good, but it's not like a monotonic increase or monotonic decrease in the percolation threshold with correlation. And the reason is if you have too much clustering, that may not be good, because imagine if you have 2 disconnected islands, that is really not going to help us with percolation, right? So we want some clustering, but if you get too much clustering, that is again going to, not give you, like the percolation threshold at some point will stop decreasing and start moving this way, right? And this is the same figure sort of drawn a little bit differently. So now, in this direction, we are showing correlation strength. In this direction, the occupied bond fraction and the G by G naught is in a color map. And once again, you can see this dip, the lowest, and then it starts increasing again, right? All right. Okay. So now that the percolation thresholds depend on C, it's not one percolation threshold, right? It depends on C. How do we go about sort of understanding these kinds of networks? So you can write this shear modulus, you know, close to the percolation threshold, right, as P minus PC to some power. So you can write it as some power law, and then there is some prefactor constant, right? And the PCs, again, are different as a function of Cs. And then you can get a data collapse like this. But the interesting thing is that the beta here is not the same for all of them. You will get a series of betas as well, right? But you can get this data to collapse in this power law form. And now if I, show basically the PC as a function. So by doing this, you can pinpoint what is PC. The whole point of doing this, if I go here, or one of the points of doing this, if you look at a graph like this, you can ask, so where is my PC? Is it somewhere here? Is it somewhere here? Where exactly is PC, right? To decide where the percolation threshold actually resides, we can do this kind of thing, right? So now once we have the PC, we can plot this PC. Earlier, what I showed you was more of a qualitative thing where you saw the percolation threshold moved. You can also check it from something which is known as the non-affine parameter, but I don't want to go into that. But this is, I think, sort of something that's easier to motivate and understand. And now if I plot this PC as a function of correlation strength, you can see that initially the percolation threshold decreases as we increase the correlation strength, but then it goes up again, right? So too much correlation, you have diminishing returns. You have a question? There is not a physical reason. So you can basically associate an emergent length scale with whatever is happening here, and that has certain behavior. But why 0.6? I don't have it maybe there is a reason, but I don't have a good answer to why that's this. Right. And then, like I said, the scaling exponent beta, that is also, not a constant. If I plot it as a function of the percolation threshold, then, it shows it falls on a straight line. Then you can analyze other kinds of things like non-affine correlations, how much deviation is there from the, affine behavior. You can look at 1-point versus 2-point correlation. You can relate this to an emerging length scale, etc., and, analyze this thing more. But the main take-home message is that initially, when you have correlation, the network can attain rigidity with less material, but then too much correlation, you get diminishing returns, right? But one of the things to think about is that, without decreasing or increasing the amount of actin, if the cell remodels in such a way that actin is more clustered versus more spread out, or differently clustered in different regions, but overall the amount of actin is the same, then the cell can sort of change or tune its mechanics just by redistributing its filamentous network and reorganizing it. So that kind of makes sense in a biological context, that this kind of spatial heterogeneity or structural correlation, it's not a bug, it's more of a feature, right, of these kinds of systems. So I guess I wanted to end at this point and take any remaining questions, but tomorrow when we discuss, this is still what happens when you have one type of filaments, but in real life, you will have multiple types of filaments. You can have motors, and somebody brought up this thing about there being, change, like crossings are not permanent, they're transient. What happens when you have those kinds of situations? So those kinds of things. And also, different types of transitions, what is the order of the transition? In a biological context. So we'll discuss those things in tomorrow's lecture. And I will take any remaining questions or comments you have. Yes.
Like percolation threshold versus like correlation to different?
So that we don't know. We have only explored this in the context of this Kagome lattice, right? So the thing is, so I don't know what will happen in other lattices, and I don't want to make a claim. One other thing we haven't done and we are doing now, like here, the structural correlation we put in by hand, right? But in reality, you can get structural correlations because of when, let's say, fracture happens, the way bonds will break, if bonds are broken in one region, more bonds will break, right? So what if you did not put in the structural correlation by hand, but you allowed external stress to sort of give rise to a correlated network? For that kind of a correlated network, what would this, reentrance look like, and where would this be? I think that's something that we are trying to understand right now. Right? So, yes. Yeah. Yeah. Yeah, it's at a very particular angle. Yeah. Yeah, yeah. Yeah, I don't have a good answer to that. So, I think from a point of view of theory, people play a little bit fast and loose with the exact angle, and they just say that it constrains angle, but not so much as, but I guess there may be some work on why, I guess, so from these kinds of theories, I'm saying that people have not looked at specific angles of 45 degrees or 70 degrees or something. Has picked that angle. So yeah, I don't know. I mean, it could also be that when the filaments are growing, in terms of how much, obstruction they will face in their growing, right? So if they're growing more, I don't know. I don't know. We can speculate. Yeah, yeah. But that's a very good point. Yes.
Maybe you mentioned that in initial, but in this work, the networks, it's a stretch and bending one or just stretching?
This has both stretching and bending, but it has spatial correlations added on top of that. And this is not on a triangular lattice. Like I was telling you, until I was a postdoc, I liked a triangular lattice. I love triangular lattices. I worked on triangular lattices. But then when I started thinking a little bit more about biological networks, it didn't make sense to start with a network where there would be 3 crossing filaments to begin with. Then, so I switched to Kagome lattices. And then most of my work after that has been on a Kagome lattice-based network. Yes. Yeah. I am not, so the thing is, some of the things I'm working on right now, dynamical percolation, there is very little work, but one of the things that we are working on right now, is about percolating networks for mitochondria. So we know that in your books, mitochondria looks like these bean-shaped structures and small, but that's really not what actually is true. So mitochondria can form like those small structures, but they can also form bigger elongated structures, and they can get connected in a network form. And these mitochondria also undergo fission and fusion and etc. So the network morphology is very, very dynamic. So some of us are thinking of that as a dynamic percolation problem. I mean, I'm trying to work on that and develop a theory for that as a dynamic percolation problem. Yeah. Other questions? All right. Okay, thank you.